Hi everyone! In this video we're going to go over physical properties of the molecules that we're covering in chapters 15 and 16. So let's start with carboxylic acids. So if you have a carboxylic acid with a small alkyl group attached, so a low molecular weight carboxylic acid, those are generally liquids at room temperature, and they have very sharp or unpleasant odors. Now, the carboxylic acid group, COOH, is very polar. And in fact, you can have two hydrogen bonds between two carboxylic acid molecules. So down below, there's a figure showing one carboxylic acid on the left and one carboxylic acid on the right. And notice that we can form a hydrogen bond between the hydrogen on the OH group of one carboxylic acid and the oxygen on the carbonyl group of the second carboxylic acid. So because we have two of those, we have two hydrogen bonds. Now, the connection between these two carboxylic acids is strong enough that we can say that it's a dimer. So a dimer is two identical molecules bonded together. This could be covalently bonded or through hydrogen bonding. And in this case, it would be through hydrogen bonding. Now, because we have twice the number of hydrogen bonds, carboxylic acids have really high melting points because we need even more energy to break apart those two intermolecular forces that are holding the molecules together. So for instance, if we compare this to an alcohol, alcohols only have one OH group that can hydrogen bond. So the boiling points of carboxylic acids are even greater than those of alcohols if you're comparing to molecules with similar weights. All right, so let's look at a chart of all of the different types of molecules that we've looked at up to this point. So on the x-axis, we have molecular weight, and that's increasing going from left to right. On the y-axis, we have the boiling point, and that's increasing going up. So on the very bottom, actually, let's just look at molecules with similar molecular weights. So I'm just going to focus on these molecules, which all have a mass or molecular weight of about 45 grams per mole. And you can see that alkanes are at the very bottom, as well as ethers. So they have very low boiling points. And remember, alkanes only have London dispersion forces between alkanes, or two of the same alkane. And then if we go up, we can see aldehydes and ketones have a greater boiling point. And that's due to the fact that aldehydes and ketones have that polar carbonyl group. So the C double bonded to O. So they have dipole-dipole interactions. Then if we go up even further, we have alcohols. And remember, alcohols have that OH group that can hydrogen bond. So that's why those boiling points are greater, because it takes more energy to break a hydrogen bond. And then last but not least, we now have carboxylic acids, which have higher boiling points because they have twice the hydrogen bonds due to the carbonyl group as well as the OH group. All right, so again, the stronger the intermolecular force, the higher the boiling point. Now, what if we mix a carboxylic acid with water? Now, we already know water can hydrogen bond. We also know carboxylic acids can hydrogen bond. So of course, carboxylic acids can hydrogen bond with water. So here is our carboxylic acid, and then we have our water molecules here and here. And notice again that there are two places that carboxylic acids could potentially hydrogen bond. We've got the oxygen on the carbonyl group. So that could hydrogen bond with another molecule that has a hydrogen bonded to either nitrogen, oxygen, or fluorine. And then we also have that OH group that can hydrogen bond as well. And remember, these hydrogen bonds are occurring because the oxygens are partially negative, the hydrogens are partially positive, so they're attracted to each other. All right. Now, we're going to skip esters because they are a derivative of a carboxylic acid, so they're pretty similar. We're just going to go on to amines, and remember that amines have a nitrogen in the middle, and you can have either primary, secondary, or tertiary amines. Now, if you do have an amine that has a hydrogen on it, the NH bond is not quite as polar as, for instance, an OH bond. So amines will have lower boiling points than alcohols. Now, primary and secondary amines do have hydrogens attached. So for instance, a primary amine has one alkyl group. A secondary amine has two alkyl groups. And then a tertiary amine has 3 alkyl groups. So primary and secondary amines have hydrogens that are available for hydrogen bonding. Tertiary amines do not have a hydrogen, so they cannot hydrogen bond with other tertiary amines. But we'll see later that you can actually still hydrogen bond a tertiary amine as long as the other amine has a hydrogen available. So let's see, we already covered that the hydrogen bonds are not as strong in amines compared to alcohols. So amine boiling points are a little lower than those of alcohols. Now, in terms of the physical states of amines, smaller amines are gases. Larger amines will be liquids or solids, and that's just due to those extra carbons and hydrogens that can create more London dispersion forces, and so they're going to pack together more tightly due to those greater intermolecular, or I guess more intermolecular forces. So looking down below, we've got an example of two amines. They're the same. And you can see that the hydrogen on one amine is attracted to the nitrogen on the other amine. So we can create a hydrogen bond between the two molecules. Now, amines can also hydrogen bond with water. So that means that amines are water soluble unless the alkyl groups that are attached are super big. If they're really, really long or really big and complex, then that's going to prevent the amine from dissolving in water. Because remember, alkyl groups are hydrophobic, so they are nonpolar, so they do not dissolve in water. But if your alkyl group's small enough, then the amine can hydrogen bond with water and dissolve. So looking at a primary amine first, notice that there are two opportunities for hydrogen bonding. So the nitrogen on our amine can hydrogen bond with the hydrogen on water, and the hydrogen on the amine can also hydrogen bond with water. Same goes for the secondary amine, same situation. The nitrogen on the amine can hydrogen bond with water. and the hydrogen can also hydrogen bond with water. Now looking at the tertiary amine, notice that the tertiary amine does not have any hydrogen atoms. However, the nitrogen can hydrogen bond with one of the hydrogens on water. All right. Now let's talk about physical properties of amides. So remember, amides have a carbonyl group and a nitrogen group. So there are a lot of opportunities here for hydrogen bonding. So for instance, the carbonyl oxygen can hydrogen bond with a hydrogen from another amide. And then the hydrogen atoms on the nitrogen part can also hydrogen bond with the oxygen from other amides. So because of all of these different opportunities for hydrogen bonding, amides have really high melting points, similar to carboxylic acids. Now, really simple amides like formamide, which is shown, or which would just have a methyl group for the R group, that is, or actually a hydrogen, excuse me, that is a liquid at room temperature. But if those alkyl groups are larger, then the amides will actually be solids at room temperature. So what if we mix an amide with water? So we've got our amide here, and then we have, again, 3 places where we can form hydrogen bonds, at least on this amide here. So we have an opportunity for the carbonyl oxygen to form a hydrogen bond with water, and then the 2 hydrogens on the nitrogen can also hydrogen bond with water. Now, what if your amide is more substituted? So here we have an amide where the nitrogen is no longer bonded to 2 hydrogens. Instead, it's bonded to 2 alkyl groups. You can still have hydrogen bonding between the carbonyl group and water, as well as the nitrogen and water. But there's less opportunity for hydrogen bonding in general. So that wraps up our physical properties section. Next time, we're going to start discussing reactions of carboxylic acids, and then we'll kind of start going into reactions of esters, amines, and amides. So I will see you then.